All right, so the meeting is now recorded, so we can officially start. Hello everyone. Welcome to the next meeting, episode 54 of Warsaw Quantum Computing Group meetup. My name is Pavel, and I will be the moderator of this meetup. And today we have a pleasure to host a great speaker, Professor Karol Bartkiewicz, and he will give a talk about machine learning and optical quantum information. So as you can see, this meeting is recorded, so hopefully the video will be later available on our YouTube channel. Karol, would you like to have this lecture interactive so that the participants can interrupt and ask questions, or we can just ask them to post their questions on our chat and we can just ask all the questions at the end during the Q&A session?
Okay, I don't mind being interrupted, so please go ahead and ask questions.
Okay. All right. Anyway, if someone would like to ask a question, please first post your question on the chat. So if there are some urgent questions related to the slides, we'll try to ask immediately. And if there are some more general questions, we'll wait until the end. So let's try to do it this way. Okay, and before we start, we would like to thank our strategic partners for supporting us and helping us organize this event, Cogit, Snarto, and Sonovero R&D. And we'd also like to thank our honorary partners for also helping us in advertising this meetup. So with this, I will now stop sharing my slides. And Karol, if you are ready, the Zoom is yours and you can start sharing your slides. And first of all, thanks for accepting our invitation.
I'm honored actually to be able to show you results of my and my collaborators, because this is already 54th episode of your meeting, and it's getting very recognized around the community. So I'm happy that I can actually join this initiative. So today I will maybe speak about quantum machine learning from the physicist perspective, because I'm a physicist. I work at Adam Mickiewicz University in Poznań. I also collaborate with people from abroad, including such countries as Czech Republic, Japan, the US. So there are many people involved in this research that I would like to talk about, and I tried to show you on the map how we actually are located. So this is the only like a picture of the globe, and we can see all the locations. Yes, so it's quite difficult to collaborate in this like multi-time zone fashion, but we are doing our best. So we actually started working on this quantum machine learning before the pandemic. So we could travel a lot, then it got more difficult. And most of our group are actually experimental physicists. I'm more into theory. Also, people from Japan and the US are also theoreticians. So people in Czech Republic perform experiments. Okay, so I work in Institute of Spintronics and Quantum Information, so I'm not into spintronics, but I am actually into quantum information and specifically optical quantum information. So probably you already know that quantum history of quantum physics, more or less. So I have a timeline. Actually, here we started in early 20th century, and there were many discoveries along the way. And in 1905, Einstein discovered quantization of light. So light was actually one of the first, let's say, things to be considered as quantum. And actually, then we still work with light because it's very pleasant carrier of information, because it's hard to interrupt the information encoded in light. Usually it's hard, okay? And also in Poland, we have a long tradition of quantum information theory. One of the pioneering works on this was by Professor Roman Stanisław Ingarden from Nicolaus Copernicus University in Toruń. So it was published in 1975. So already then in the 70s in Poland, we were actually studying quantum information theory. So this was not that popular in the 70s, and we already started working on this. Okay, so up to like 2013, physicists were mostly involved in solving some typical quantum problems, but then in 2013, machine learning started to be very popular due to technological progress, as you probably all are very well aware of. And then people started to think, okay, so this is so important, so why not to try to do this better with quantum physics? And it happened that in 2009, Harrow, Hasidim, and Lloyd, they proposed an algorithm to solve linear system of equations. So as you probably already know, like linear algebra is the bedrock of machine learning. So you're able to solve algebraic problems faster with quantum hardware and software. Probably we can do also machine learning better. Okay, so this is more or less like natural progress which leads to a situation where we actually are getting interested in quantum machine learning, and many institutions and companies are actually conducting research in this direction. Many of them actually are also producers of quantum computers or very serious research institutions. Okay, so just to give you some background, if you like to know why actually just do machine learning. So there are many reasons for business, for example. So one of them is actually like ads recommendation. Probably you already are familiar with this, but like time of arrival estimation for like Google Maps and other things like that. So or ChatGPT, I forgot to add it because this is an older slide. So definitely there are many applications. So so can we do machine learning better with like utilizing some ideas from quantum physics, or vice versa? Can we do like quantum physics better with using some methods of machine learning? So probably, as you can suspect, the answer is positive, but there is also some, let's say, purely physical motivation for studying machine learning from like a physicist perspective, is energy consumption. Okay, this is very important because like data centers and large computational let's say machines, they consume lots of energy. So in some cases we can decrease this consumption by several orders of magnitude if we construct dedicated hardware, especially in quantum domain. It seems that this energy consumption is very limited. Okay, so this is very important. This is probably more important than potential quantum speedup that is not that interesting for now, because it's still beyond our grasp because of this hardware limitations. Okay, okay. So if you want to speak about quantum machine learning, it is good to have some, let's say, okay, some idea what to call what, because there is a lot of confusion. Okay, so there's this graph on the right, okay, and it shows you that we can actually have different types of machine learning depending on data generating device and data processing device. And some people call quantum machine learning like type of problems that's not strictly quantum. You just want to solve some classical, let's say, mathematical problem using quantum hardware and to see if it's can be done better or not. Then this will be in our scheme. In this graph, this will be called like CQ problem. So we have quantum computer. This is the second letter is Q, but classical input. Okay, so this is CQ problem. So typically people are interested in the CQ or QC problems, but from like the research perspective, if you do like basic research, it's also interesting part is like, so what is this QQ domain? Can something interesting happen there? So this is something that we investigated in our group for some time, and I think that still there are many questions, but we have some, let's say, promising results that that suggest that we can do something that is quite counterintuitive in this QQ problems, for these QQ problems. Okay, so just to show you an outline of typical approaches, I will just maybe start with something simple, and then we'll gradually I will gradually discuss more complicated problems. So usually there are two main approaches to solving highly nonlinear decision problems. Okay, so one is using kernels, and the other is using artificial neural networks. So in quantum domain, this requires like quantum artificial neural networks. This is something that has many layers, as you can probably imagine. And if we have very complicated computation, this is very error prone. So alternatively, we can expand our space to have larger, let's say, this latent space and perform very simple computations. And expanding space, operating in high-dimensional space, is something that quantum computers can do very well. Even today's hardware can achieve this. We can have huge computational space with very few operations, which are moderately good, and still we can do something useful with this. Okay, so it seems that for now, like this, using quantum kernels seems to be very promising. So this was the idea some time ago to use quantum kernels. Okay, so there is this famous Nature paper of 2019 where a team from IBM showed that actually this quantum kernel approach can be very beneficial. And also this was already investigated theoretically before that, and we actually performed an experiment related to this also in 2019 and wrote a paper about applying quantum kernels to solving some problems. But unfortunately, at that time, there were many papers from large groups, so we had some problems with like publishing this very fast, and finally it got published a bit later. And what was the difference here in our paper? So the first thing was that we actually used optical quantum information. We did not use superconducting hardware as it was done by the team from IBM. And we also didn't use this, let's say, Gaussian state approach that was proposed here in this paper by Schul and Kieler. And before that, it was also considered theoretically by a group of theoreticians, but this paper was, I think, from 2017. It's not listed here. You can find it because it's cited in every paper listed here. Okay, so this is something that I think is very interesting, and we can show we can solve some practical problems with this kernel-based quantum machine learning using the support vector machine method. Okay, so this was actually invented in the 90s for similar reasons that we actually use it for quantum computers. So we didn't have huge computational powers, but we had some memory to spare. So this was the reason why to use kernels and support vector machines, okay, instead of neural networks. Okay, so neural networks are also heavily investigated. There are many papers on this. I just listed the ones that were published around the year when our results were ready. So what's actually what's about this kernel approach that's like where's the magic? Okay, so the magic is that actually you change the space in which you have your classification problems. So you have like white and black dots. The decision boundary is here red. And you find such a map to this feature space where this set of points is linearly separable. And then, as you probably can imagine, then you can just solve this analytically. You can find this boundary just by a very simple optimization procedure. So if the set is linearly separable, then you're actually done. Okay. But it happens that this is very nonlinear. You have to have a very high dimensional space. So this is actually satisfied. Okay. So how to do this? Well, the thing is to have some sort of a kernel. So the kernel is this kappa function here. So you have one, let's say, point for which you want to compute this kernel value. You have some other point. This is mth point from, for example, from training set, and you just compute the kernel. And this theorem says that this boundary, actually, this line in multidimensional space is given as this has this form. Okay, so there's a kernel and some parameters am, which are actually can be efficiently found using linear programming. So this is very once you have kernel computed for the points, this is very easy to find. Okay, and so how to actually compute this kernel? So in quantum physics, this is actually done for free if you prepare a state and measure it. Okay, so this is this corner. So if you prepare, let's say, state psi of x, okay, parameterized by x, and you project it onto the detector, which is parameterized by x prime, the frequency of such events will be proportional to this kernel value, okay? And essentially, if the state psi x is parameterized in some non-trivial clever way, for example, like this, then this kernel can have nice properties and can be useful for machine learning. Okay, so this is some example generated using Python that we have like two sets, red and blue. So you can see that one of some points are more translucent than the others. So one is training set and the other is the data set. Okay, so we training set and the other is test set. So we can actually try this works, and then maybe perform an experiment to see how well we can do this in realistic conditions when we have some noise, some losses, and so on. Okay, so let's take this set. This is clearly not linearly separable. We cannot draw a line that separates this, so we need some higher dimensional space. And this is one of feature maps that we can find. Okay, so if you just go to literature, you can see that there are some standard kernels. For example, the cosine kernel, you can take powers of it to make it like more condensed. And exponential kernels, some polynomial kernels, these are the most popular ones. And it seems that up to some point, people just use some very naive approach in the literature. They just thought, okay, so if I want to have this cosine kernel, I will use this sort of an expression, and then the number of qubits that I need to encode all of this, because this is k, so this is the number of k just numbers, the orthogonal states that I have, is just, it's d times n. Okay, so what is d, what is n? So n is this power here, and d is the dimension of the problem. So it's a two-dimensional problem, d is 2. Okay, so this seems like overkill. At least it seemed to be an overkill for us. So we did some thinking and we thought, okay, so if we just modify this expression a bit, we can actually reduce the number of qubits required for computing this sort of a kernel by a lot. It is exponential enhancements actually in the sense of the required qubits. Okay, so this is this is just like algebraic trick, and it seems that we can do this. So there are like two lessons from this. So one is that actually if you just take an expression from literature, probably it's not the optimal one because nobody bothers to find the optimal one. And the other is that we can use exponentially fewer qubits for, let's say, computing the same sort of a kernel. Okay, so this is important if we have finite, say, feature space, or we have a finite number of qubits available. Okay, so this is one observation that is very important. So the other is that actually these amplitudes. Okay, I will just go back a few slides here. Okay, so this is a feature map. Okay, here are some amplitudes for the states. They could have various forms. Okay, and in physics, usually if we think about some superposition like that, so we like to imagine, okay, where does it come from? So one explanation could be that we can use like a multi-slit interference states, so they are called like MSI here, and then so you just have like a many slits on a glass plate, and for example, you reflect light from it, and this is if you want to identify the number of the slit which it comes from, this is actually the numbered with n. Okay, so so this is one way of doing this. The other one is just to think, okay, we have a squeezed state. So in this is a special type of superposition of like 0 photon, 1 photon, 2 photon, and so on. And the squeezed states, they have sometimes have parity, parameter, but never mind that. The important thing is that they are highly non-classical states. From them you can generate entangled states, and they are also a standard resource in optical quantum information processing. And if we just forget about this higher photon number components, so we just limit ourselves to 9 and 14 photons, let's say, and the rest has too little, too small amplitudes to be relevant, then we can also see how we can encode, let's say, kernels using this feature map. Okay, so there are many physically motivated ways to do this, and the optimal one, in the sense that it has the highest resolution for the smallest number of qubits available, is this blue curve. Okay, and we just found it by numerical optimization. So it's just depends on n like this. Okay, so the others are just like physical states that you can generate quite in standard way. Okay, so this is like theoretical motivation, but once you go, for example, to Czech Republic and visit our lab there, you can see that, okay, this is now you have to like build something from parts as depicted in the picture. And so finally, you want something non-trivial, okay? You don't want to have like just one photon interacting with the other photon and in some very trivial way. So you need more degrees of freedom to encode higher dimensional space. And using photons and optical quantum information, we usually encode qubits using polarization or spatial degrees of freedom. So polarization, this is, for example, H polarized single photon, like here and here. And then by using half-wave plates and quarter-wave plates, you can rotate this polarization to some other polarization state. Actually, by using this combination, it can be any let's say, any state. There's some optimization done in this figure because actually we need 3 plates to actually say that this is completely complete U2 group, but this is but definitely this the expressive power of this setup is as high as it can be. Okay, so this H-polarized photon, it can be like, so we can introduce some relative phase between these two photons. We can rotate the polarizations independently here. We can then expand the space of the states by using beam divider. So this is like birefringent material where H polarization goes horizontally, and this V-polarized component is diverted upwards. And then we have additional degree of freedom. So we call it like top and bottom line. Okay, so already from 1 qubit state, we have 2 qubit states. So this is like H-polarized photon in top line. This is HT. H-polarized photon in bottom line. This is HB. And there is also V, VB, and so on and so on. Okay, so there's a product because we have these two components repeated, but they're also interfering here. So we can also include some interaction which is necessary to show that this is not purely classical computation, but we have to we have some benefit from using single photons. Okay. Okay, fine. So how does it work? Does it work well or moderately well, or what can we do about it? Okay, so we have some input data. We want to test it, and depending on this power here, so this is like a square. Okay, so this is like just cosine kernel. So using cosine kernel, we have this. So 82% of points are classified correctly. If we use cosine square here, so 90% of points will be classified correctly. So for this pattern here, situation is different because it actually gets worse if we introduce higher powers here. So you see that this is some sort of a hyperparameter for machine learning that has to be optimized to get the best result. Okay, and we can actually do the same using our setup here. So we, for the point we computed the kernels, you see that these edges here are a bit perfect in comparison to vertical ones because of experimental errors. And actually, just by accident, because we used few points because didn't want to like overdo it with this experiment. It takes some time because all the points are mechanically, or the plates are mechanically rotated. So if we have many pairs of points here, so this will take forever to get this with high resolution. So for this, also the test set was rather small, so we have like 92% here. So this is just like a question of a few points close to boundary that are classified a bit differently by this kernel. But for other patterns, this actually is the same as a sphere. Okay. Okay, so this is how we do like this proof of concept experiment. But what about like real problems when you have thousands or millions of parameters where you have to decide about some more complicated functions? Okay, so the approach that people actually use for the expand Hilbert space is just to stack these beam dividers in this way. So so this is, let's say this was one layer of optical quantum computer. So you have to use multiple layers to expand the space. The operations are trivial because this is not like interaction between qubits. You just have to be sure that your setup is of high quality. And this is I probably have to update this because this is from I think 2 years ago, this information. So depth for quantum optical computing setup. So we have like 12 or 24 spatial modes. If you take a look at Xanadu AI. So this is, so you can see that you can get quite huge space, even with like current optical setup. So this still is quite impressive that you can do this nowadays. And if you want to analyze this theoretically, it's because for now I showed you how to use like standard Dirac notation approach to analyzing the circuits. Probably there are much better ways for higher dimensional systems. This is something that is based on tensor network, this formalism, and using, for example, matrix product states. So there are many examples of people using this formalism for related problems. Also in solid state physics, this is also very popular formalism. Okay, so tensor networks are, some people claim that because of applications of quantum physics in machine learning, they're like linear algebra of 21st century. So probably this formalism will be as important in this century as linear algebra was before. Okay, so I'm not sure because this is also linear algebra, but some people are promoting this using such catchphrases. Okay, that's still it's quite important, and it makes things easier to analyze. Okay, so the thing is like about computational complexity. Is there like any potential speed up for like for performing feature mapping and so on? Okay, so it seems that there is there is some speed up if we can prepare arbitrary states efficiently. Okay, so this is like this 1 over log complexity. This is Grover-Rudolph algorithm which works well under some conditions. Okay, it does not always work efficiently. And this is a paper from 2011 where this is like church-Turing, let's say, equivalent for noisy quantum states computation that sometimes it's not efficient. Okay, so this is conditionally there could be a speed up. Okay, but the speed up is order of like logarithm of this product of dn. Okay, so this is just the same thing like restated. So for people who are more interested in like basic research than industrial applications, the more important question is actually can we actually observe quantum advantage in the expressive power of quantum kernels? Okay, so this is a question for like basic research, and this is probably for people who are more have more practical attitude. Okay, and this is still a valid question. Many people are working on this. So can we actually use to express let's say more difficult patterns using quantum computers and cheaply in comparison to classical computing. Okay. All right, so this was our modest setup from, say, Central Europe. This is built by a Chinese group who has unlimited resources in comparison to us. You can see that the number of elements is much higher, and this is a quite new result. So using optical quantum information, this computer, I don't know how to pronounce it correctly, so I won't attempt, but this is the name of this quantum computer. Is claimed that it can perform some operations used for machine learning 180 millions faster than the world's most powerful supercomputer. So obviously one should take this with a bit of skepticism. Such claims are done from time to time by many groups. Usually it turns out that the classical computer, the estimation of the time that it would take for a classical computer to do something is overestimated by like order of magnitude or more. So, but here, if this is even like several orders of magnitude lower, still this is quite impressive. Okay, And what is the problem here? So this is I don't think that I know the details, but if I remember correctly, this is related to random tree search. Okay, so this is if you have huge space and you want to sample this space, if you use that many elements, you can probably do this more efficiently using classical computing. Okay, so this is the power of quantum physics. So you can, starting with a single photon, and because of the number of configurations in which you can find it in final step grows exponentially, you can outperform classical computing for some sort of sampling problems. But it strongly depends on the precision for which you want to have this, okay? Because if you don't want to have perfect precision, probably there exists some classical algorithms, some sampling classical algorithms that can give you an approximate answer in reasonable time, okay? Okay, so back again to some very elementary examples. So in machine learning, we have, let's say, also other problems that other than, let's say, making decisions in the form supervised learning. So we had labeled sets in the beginning. Now we can consider unsupervised learning, okay? So this is an example of the CQ machine learning. So imagine that you had some classical data and you want to use quantum computer for, let's say, finding clusters. Okay, you just want to use some well-known algorithm like k-means clustering, and you just want to compute some centroids and update it as it's usually done in this algorithm, as it's shown this animation. So what is the computation that's behind all of this? So what you have to do, many times you have to compute distance between points in usually high dimensional space. And what you can do in physics, instead of computing distance, you can measure distance, okay? So if you just choose a proper metric for quantum states, probably this can be measured in a very efficient way. And this is what we demonstrated some time ago. We selected Hilbert-Schmidt distance, and we encoded information not in the density matrices that describe quantum states. So density matrix does not only carry the information that about like superposition, it also carry information about coherence. So we don't use information, strict information encoded in some amplitudes in front of some vector components, like you do in a standard quantum information processing, where you want to have your coherence always perfect for as long as you can, and then you are satisfied with your results. Okay, we intentionally sometimes like decrease the coherence because this allows us to encode more parameters. So density matrix has, if you take a superposition, it has, for example, n parameters, and density matrix has something that's proportional to the square of these parameters. So you can just pack more information in if you use coherence terms. Okay, and moreover, independently if these are pure or mixed states, so you describe them by density matrices, this Hilbert-Schmidt distance can be measured relatively in a simple way. Okay, so what is the benefit of this approach? Okay, so first you just have to observe that there are like 3 physically measurable quantities if you just expand this, and you can just measure 3 of them. And this is independently of the dimension of your problem. So you just have to perform 3 experiments for each term here. And for example, you have to those are like positive operator valued measures. So 4 POVMs per observable for 2 qubits. Okay, so number of so this is So this is the number. So this is the number of parameters that you can encode. Okay, so you have a 2-qubit state. You can encode 15 parameters in it. These are like parameters that actually have to fit in a ball. So it's not like a full like 15 parameter space. So it's not like a cube, hypercube. This is like a hyperball. So but nevertheless, they're more or less independent. Okay. And the complexity of this Hilbert-Schmidt distance measurement, it's like a logarithm of this n, or d squared, where d is just a dimension of usual Dirac vector. Okay, so and if you compare this to classical distance computation, which is not bad because it's polynomial in n, this still gives you some potentially some speed up. So asymptotically, this should be faster. Okay, so we have some sort of a proof of asymptotic quantum speed up. This is if you use this approach. This approach was already like thought of before, so it's not like our invention, but we actually performed experiments using quantum optics for measuring these quantities. And also usually people use just swap test to perform distance measurement between pure states. So the new thing is that actually we also thought about coherence and how to include it here. Okay, and this sort of analysis was also not performed. So can we actually how we somehow compare quantum and classical computation for this? And for those of you who actually are familiar with experimental quantum optics, how we perform this experiment is more or less given by this picture, where a laser just pumps two nonlinear crystals, and we get a pair of entangled photons. Okay, and we use hyper entanglement. Okay, so what does it mean? There is spatial encoding between, there are actually like two states. Okay, so one is row 2 and one is one's row 1, row 2. So like two copies of the same state prepared in the setup, but one is encoded in spatial encoding. So this is like top bottom spatial mode, and the other is encoded in polarization encoding. So this is basically H and V polarization. So this is hard to like get from this picture. So this is why two pictures, but physically there are just two photons. So there are two energy portions here, A and B. They are just like prepared in this very, let's say, clever way to make this experiment more efficient. Okay. And if you have just two photons, then you just count coincidences of them for specific detector configurations, and this works very fast. And for like 15 parameters, we don't have we cannot code every state with this setup because of this approach of using hyper entanglement. But definitely, it's very efficient for the class of states that we considered. Okay, and if you just it's a relatively simple setup, but still there are some experimental errors. So the blue curves show you the experimental results, while the black ones show you what we expect from theory. And we prepare something like a mixture, statistical mixture of Bell phi minus state and HV state. So this is basically like 0, 1 state, and this is like 0, 0 superposition with 1, 1. Okay, so there's some admixture statistically, you can have 0, 1, okay, which is not in the superposition. So this is Q parameter, so this is weight of this component, and here, and this is the second state. So we measure distance between these two states, and there's P parameter on this vertical axis, and this is how we actually what we see. Okay, and just to analyze errors a more convenient way, we use square of the distance because it allows us to like show the errors in a user-friendly way. And some experimental results that maybe are not that interesting. Okay. But what's interesting is maybe the error robustness of this approach. So it seems that if you have like, okay, these are like two clusters generated at random from Gaussian distributions to the Gaussian distribution. There is no distance error. So this is how this k-means algorithm would work if you just wanted to have two clusters. If you allow for some distance measurement error, some let's say difference between the perfect case and a bit noisy case would be visible here. And if you actually allow for more error, this will be more noisy, obviously. Okay, so we in our experiment we had this slightly let's say moderate error, but so it would still be useful for some applications, but it's definitely not the perfect case. So and so this this is actually everything about this clustering approach. Okay, so this is so what we had so far, we had classical data. We fed the data to quantum instrument, quantum optical instrument, and then we tuned this instrument to have some let's say useful outcomes, or maybe we even just used raw data and then processed them on a classical computer to do something interesting with this. Okay, but what about like instead of doing this way, we just do it the other way around? Okay, so this means that we have some classical computer that will feed information to quantum setup, which we expect to perform some quantum operation. So what quantum operations are possible? So some of them are quite interesting, like optimal cloning. This is the best approximate performing the best approximate copy of a non-quantum information. So we just decided, because we have a lot of experience with optimal quantum cloning, to try to train a setup using this classical control approach to perform some function that will that its quality, its fidelity will be actually give us some reward for the system. Okay. And if you just have a look at the complexity of the problem, depending on the size of the quantum register that it's on the input, it will turn out that this distribution of probabilities at the detectors is given as something proportional to permanent of unitary matrix that describes this operation. Okay. So this is related to boson sampling problem, which is computationally hard, and this is something that is sometimes leveraged in optical quantum computing to show that we have some advantage over classical computation. Okay, but here this is we performed quite simple experiment, and it allowed us to compensate for many experimental imperfections. So we are not able to model this setup perfectly, but if we use classical control for quantum setups and we want to train them to perform the best quantum operation, we know what are the physical limitations for this quantum operation. So we know how close we can get to this let's say perfect operation of the device. We can go quite close, much better than using manual let's say setting, and we actually tried to let's say show that this is that this approach is very fruitful for experimental physics, especially in optics. Okay, and so we're quite happy with this result, and also because we went deeper into classical machine learning and we understood more and more, we discovered that actually instead of like recreating all the results, like we already knew what is the optimal quantum gate here. We just wanted to see if we can build a setup that can optimize it. We decided to search for problems that, okay, we don't know what's the solution in physics, but maybe with deep artificial neural networks, we can find some new results or can see how much we are missing from the picture. And it turns out that in physics, there are quite a few such problems where we have no idea what would be the solution, or we just have some analytical solutions invented by very clever people over the last few decades, but still they are quite far from the optimal solutions found by ANN. And this is encouraging because sometimes it appears to us as physicists that, okay, we cannot invent something okay better than this guy, but if we know that there is some very, let's say, convoluted neural network that gives us better results, probably it can be explained somehow. And we search for these explanations and we want to formulate some law of nature based on that. Okay, so it seems that ANNs become like some useful tool in quantum physics. So this is like a very simple example from hard problems entanglement detection. Okay, so imagine we have two pairs of entangled particles, and we allow only blue particles to interact, and we measure the outcome of this interaction. And here we perform some single qubit operations on these particles. These are qubits. We can just have two copies because we want to not only to measure local, let's say to perform the tomography of this state, but maybe get some nonlinear information about this the state. So usually we always build statistics. So we have either a train of some states, so they appear with some frequency in time, or they are like pairs prepared and available at the same time in some special configuration. So anyway, we can if we have like a source of entanglement, we can one of the pairs can be just kept in some sort of a loop and then utilized to perform this experiment. Okay, so if you just perform some such experiment like that, where just like the entanglement swapping for quantum repeaters, so you can imagine this step on the right. You have some coincidence logic, use artificial neural network to classify this state as entangled or not. You know what state was prepared because you designed the state. You can check what are the usual criteria that are used for deciding about entanglement of particles, and usually they are invented such that there is this type 1 error. So the error that will classify separable state as entangled is 0. Okay. But not all entangled states are recognized as entangled. So this is type 2 error is like 14%, and the success rate of like fully entangled fraction, for example, this is one entanglement let's say witness that can be used here, has quite high success rate, but it requires n equals 12. So here capital N requires this is the number of configurations for these rotations here, and if this plate is inserted on or removed from this setup. Okay, so you have to have 12 configurations. So if you just have a look at this, you can see that success rate ranges from 86 to 46 for the best known entanglement witnesses. Even if you use them jointly, it's still worse than, for example, the similar thing that we do with ANN. So where the success rate for 12 measurements is like 92%, okay, much higher than any of these. Type 2 error is 8%, okay, so, and this type 1 error is about 0%, okay, so still we don't understand everything about 2-qubit entanglement, which seems to be trivial, but in this setting, ANN can tell us something more than like analytical approach based on some physically motivated quantities, okay? So maybe there is some deeper physics here. So this is what we are investigating at the moment. So we are investigating this trade-off between sensitivity and selectivity of entanglement witnesses for even for 2-qubit states, which seems to be like a solved problem, but still it is something more that you can learn from ANN. Okay, and also, okay, let me see what's the time. Okay, well, we'll not maybe go to details, but what's the next motivated, let's say, experiment is to try to, for example, to forge quantum money. Okay, so quantum money is just a sequence of qubits that has prepared in secret by basis. So, and you want to basically have some sort of a street where you keep zeros or plus minus states at random configuration. And definitely there is some algorithm which decides how these states are prepared. So the question is, can we like mimic the behavior of this algorithm, and can we emit our own money? So, can we actually learn about something about this algorithm from like destroying randomly some portions of qubits and storing their serial numbers here? Okay, so we did some research on this some time ago. I actually wrote some program that just uses a very simple this convolutional generic serial network to generate the images from some samples and to see if they're actually just like a stupid experiment to see if they are similar to what would generated by some hash function here. Okay, obviously this is something that requires detailed analysis, but in the end it's not that similar. But I just wanted to see if I can do some generative machine learning on my own. Okay, so this was just like a small exercise in using some more complicated machine learning algorithms. But in the end, I was left with this question. Okay, so this is still classical machine learning. So can we do generative machine learning better with? Okay, can I raise this? Okay, so I think that somebody did this. I didn't do it, but never mind. Okay, so I hope that this doesn't bother you. So the question that I was left with was, okay, so can we do generative learning with quantum computers in a different way than it's done with a classical computer? And it seems that like this very prominent approach that is used widely is generative adversarial network approach, when you have like two networks, you have generator and discriminator, and they just are trained adversarially to each other. Okay, so you have real data samples, you train discriminator to decide if something was sampled from real data set or from generator. And by backpropagation, you train the generator, which also has some entropy source here, so you can have some random numbers used. Okay. So this is a bit different than, for example, this stable diffusion approach, but this is still this is very interesting algorithm. Okay, so once you're done training generator, it seems the discriminator is fooled more frequently. So now we have to train the discriminator the other rounds to work by backpropagation to make it work better. Okay, and this goes and goes on in rounds. So the question is, can we avoid training this in rounds. And it seems that in some cases, yes, but if we have quantum data and quantum information and the process is reversible, then we can, for example, by using, this is not strictly like optical quantum information, but they are transmons and they are driven by microwave fields. So this is quantum computer by IBM. So can we use this computer? This is semi-optical experiment. So can we use this computer to show that we can do generative learning a bit differently? So we can do this. And the question, so first we have to like invent some ansatz for discriminator and for generator. So and it is constructed in such a way that we can actually measure something about this. Okay, so this is discriminator. So I have this real data generator. This is discriminator, and if this is real, it should give me 0, and this is inverted preparation of the states. So if all of this is it's prepared in 0 state and it's projected on 0 with 100% certainty, this means that okay, we are satisfied with the outcome of the discriminator and for real samples. Okay, and this is G is for generator, so we can do the same and see the quality of the generator can be measured like this. Okay, and to see what is the quality of generator, we can just compute overlap between real states sampled from real distribution and this G that we want to somehow learn. Okay, this lambda is just for labeling some parameters or classes of different states that we want to keep track of. Okay, so if we just do some algebra, we can combine everything to one circuit. Okay, if everything is reversible, and actually we don't need a copy of this real state generator. This is very good because, as we know, we cannot perfectly copy unknown quantum states. So this is like a source of unknown quantum states. We only have one source of this state, and say it just goes forever and just generate something. So if it goes forever, probably we can just make tomography of this. But the other approach to learn how this works would be just to use this discriminator and generator. Okay, and basically, a generator should mimic operation of this, and discriminator should allow us to learn something more about how R is prepared. Okay, and then G is, you should aid G training. Okay, so if you construct something like this, this resembles autoencoder. Okay, so if we are able to solve autoencoder problem for quantum systems, probably we can also solve this quantum generative adversarial network problem because it seems to be equivalent. Okay, and the same setup, because this has rather large depth, it can be transcribed into this swap test version where you just have 2 copies of this one actually are under each other here, and there's some controlled swap here. This is why it's called swap test version. But controlled swap gates are very complicated, and this high-dimensional state, this will also introduce many controlled gates that can be not very efficient to implement. Okay, so depending on your hardware, one of these 2 approaches can be better on the other. Okay, and you have to obviously construct a very nice cost function for it to like optimize in a stable way. So we just this is like a very general approach. So distribution of parameters, discriminator, and generator overlap. So this is something that is measured, this part, and this one is just classical distribution. So we can just tune them classically, and this is these weights here are given by some measurements. So the problem is that if you want to like build perfectly, let's say, fully capable like quantum gate, universal quantum gate that performs everything, it's very complicated to build it. So there are many approaches to this. So n-qubit unitary just can be like performed constructed in this way. This is what we did in our simulations. There are other approaches, more efficient approaches that are problem specific, like this one by Kandal and others published in Nature. So if you have some motivation and some knowledge about the structure of the problem, this is very helpful to make this circuit simpler, okay? Because this is for n-qubit unitary, and we want this discriminator in principle to be some sort of like a general function, and this generator G also to be quite general. So this is why we used this. But if we didn't want to have like just for principle experiment, but to perform a problem specific experiment, then this could have been much simplified. So this is the worst case scenario version. Okay, so we used this approach, and what we wanted to do is to just prepare like balance superposition just for the first experiment, and to by our generator, and then to train our setup to first distinguish between this the generated and these mimicked states, and they are like red and green points that show you the discriminator. Okay, this characterizes this discriminator, this overlap. So quality of generator is given by fidelity function. And we performed an experiment on real quantum hardware, and we wanted to see if it works or not. So for very simple case, it works. The depth of the circuit is about 20 so for this, so it's quite large anyway, because this is very general approach to unitary gates. And this is our cost function. So you see that it actually drops, okay, and up to some point where it actually just fluctuates up to this precision of this experiment that we can have, and fidelity just rises. So it's basically the experiment is done around here where fidelity cannot be improved, and cost function is just fluctuating around 0. Okay, so this is just for random initiation of this network. And we performed simulations for higher dimensional states. So to compare like direct counterpart of generative adversarial networks and this synergic quantum generative network that we called like that. And it seems that each time we need fewer function evaluations to reach similar quality of our results. Okay, so if so this J is not shown here, but if you want to say which one is which, so QGAM is trained in rounds. Okay, so this means that sometimes the quality of generator is improved, sometimes the quality of discriminator is improved, but they are adversarial. So if green is improved, okay, so sometimes it happens that one is improved slightly and the other is decreased. So if you see some jagged line like this, probably this is QGAN, and our approach is more smooth. Okay, so but sometimes it just converges a bit slower than the other one. Okay, so we performed many tests. This takes forever to run for large dimensional circuits. So for 5 qubit states, there's this trend that we need fewer function evaluations using this approach. Okay. Okay, so now just conclusions. So as you see, there are several types of quantum machine learning that we can call them like that, and they involve this type of data generating device and type of data processing device. And for each of them, we have some results. We try to investigate them at the same time. And everywhere there are some things to do. So, for example, here for this classical quantum, we were able to show that we can we can enhance kernel resolution for this future map. So in terms of using fewer qubits to get the same kernel that people considered before. And quantum kernels could be in principle evaluated much faster than classical kernels if we have efficient state preparation algorithms like this Groover-Rudolph-like algorithm. For this classical quantum approach, where we have this is for unsupervised learning for clustering. If you have Hilbert-Schmidt distance-based classical quantum machine learning, you can asymptotically go from polynomial distance calculations to logarithmic complexity for distance measurement, because we physically encode something and we have this distance calculation. Okay. And this is a quadratic enhancement in terms of information encoding if you use also coherence in density matrices instead of just parameter amplitudes for superpositions. Okay, so if you go the other way around, you have quantum data generating device and you have classical control or classical machine learning, then you can use this boson sampling and classical control to demonstrate how to train a quantum device to perform a function that you are interested in. Okay, instead of optimizing its performance classically, that would sometimes take forever because this distribution of probabilities of your device or the outcomes is predicting it is equivalent to solving a boson sampling problem that's computationally hard. Okay, so and also we using quantum data and deep artificial neural network, we can show that some established results in physics can be proved. So these are like very encouraging results, and this is the summary for this generative learning. And we actually have this approach that is hyperparameter free. It requires very few hyperparameters that allows you to avoid training QGAN in terms that can be more stable and it's easier to tune, because if you overtrain or undertrain generator of this discriminator, usually for this QGAN, your learning becomes unstable, and finding the correct parameters also is additional cost that is not considered here, but we spent a lot of time for fine-tuning the algorithm so that it would work as good as possible for the examples that I showed. Okay, so and most importantly, this is physical limitation. So if you use this synergic approach, we don't need two copies of the input state. Okay, so possibly we would have to use the two copies if we wanted to use interns. Okay, if we wanted to use the same data to train discriminator and generator in turns. Okay, so this is something that happens in the realm of quantum machine learning. Not everything is possible. Some things became equivalent to other things, and something strange happens. Okay, so this is usually this is why it's from especially like basic researcher perspective. This is something worth considering. Okay. Okay, so finally, I would like to acknowledge the funding that we got over the years that this research was conducted, and I wanted to show you how we met during the pandemic. At least this part of our group that we met in a park in Poznan, and because it was forbidden to meet in closed spaces in large groups and so on because of many anti-pandemic regulations. So we thought, okay, this is like going back in time into Athens, where we had with like researchers or maybe scholars were discussing their ideas in this Platos Academy. Okay, so but still we were able to complete some projects even despite this limitation. Okay, so thank you very much for your attention. I'm not sure if there were any questions during the talk, but if there were, I can answer them now.
Yes,
Okay.
so thank you, Karol. Yes, there was one question on the chat, so let me just read it. It's from Surya. I'm afraid that Surya has left, but let's read the question. How is the overfitting scenario different in quantum machine learning and classical machine learning?
Overfitting scenario. Okay, I probably have to ask some additional questions to get it correctly, but we try to avoid overfitting. Okay, because definitely it's easier to overfit in quantum space where you have many parameters. Okay, so you have to be careful with not using too large space. And you can also include some regularization. So it's I would say that from my perspective, this is very similar. Okay, so these two problems, the classical and quantum overfitting problems, are very similar. Okay, I don't know if there are like quantum approaches to deal with overfitting, but this is actually a good research question.
Yeah, it's interesting actually because so now I'm thinking that one of the ways to avoid overfitting is dropout, for example, which is one of the probabilistic methods in classical machine learning. So maybe in quantum computing, I believe that if we have quantum machine learning, it is possible that it might be easier to prevent overfitting actually. Maybe an yeah.
I think that okay, the thing is also the question is related to some notion of quantum perceptron. Okay, so the thing is that if we had some nonlinear let's say perceptron that has some I would say activation threshold, then probably this could be done in a very nice way. But what I discussed so far, this was just everything was linear, so there are no like
Okay.
activation parameters. Okay, so this is why we cannot like discuss this dropout.
Okay. Yes.
Mhm.
All right. Do we have more questions? We have more than 20 participants now. If you have any questions, you can also raise your hand first and unmute already. So in the meanwhile, maybe I'll ask one question. So do you maybe have some suggestions for people, especially young researchers willing to enter this quantum machine learning field? Are there maybe some interesting open problems that seem to be low-hanging fruits, for example, or do you maybe recommend some readings?
Okay, so well, actually I attended some workshop for it that many young people actually showed some results on quantum machine learning, and the usual thing that people start with is just take some classical machine learning problem and try to like translate it into quantum domain. And such results are not always easy to publish, but they give you some ideas. This is, I think, the fastest way to learn how to do this. So one was about, I think, very interesting by a guy from Verona about using facial recognition using quantum computers some time ago. And this is a very nice problem to start with if you want to learn, because it basically is graph related. So you can learn how to represent a graph as a Hamiltonian, and then how to solve some quantum optimization problem. And this is the typical approach to like discover quantum optimization, to apply quantum optimization, because this is probably it's somehow related to max cut problem at some point. So anyway, if you want to just dive in quantum machine learning, just I would suggest just finding just really toy examples and try to do this on your own. This is one thing. The other thing, that there are some resources to go to. One is this book by Maria Schult and Francesco Petruccione. This is Quantum Machine Learning. This is changed title because before that it was titled Supervised Quantum Machine Learning or Machine Learning on Quantum Computers, something like that. But Maria Schult and Francesco Petrocione are the authors for this book. There was also like open book by Peter Witek, Quantum Machine Learning. So this is yes. So this lady is on the other for the book, and so books are really nice because they give you like an overview of everything, and you can put problems in some broader context. So you are not like limited to what you know if you just try to implement simple programs, but you just know more or less how people think about it and what's the terminology and where to search for something if you just take a look at the literature at the end of the chapters. So I would suggest like going to this book by Maria Schult and Francesco Petrocione because I think this is like the most comprehensible book for quantum machine learning at the moment. I'm not exactly up to date, but I use this reference very often. Okay.
Okay, great. There's one more question on our chat from Arindam. Is there an application of random matrix theory in quantum machine learning? I know it helps calculating entropy in entanglement.
Okay, so the honest answer is I don't know, but definitely there should be. Probably I'm just not familiar with it, or it's not described in the literature. So, but before I would check. Okay, if
Okay.
you wanted to answer this. Okay.
Okay, good. Thanks. Yeah. If you find something, you can send me an email and I can forward it to Arindam. Okay.
Okay.
Good. Thanks.
Okay.
All right. Last chance to ask a question. I don't see any question now, so I think we can conclude and we can finish. So, Karol, first of all, thank you once again for giving this great talk and also answering the questions that we have. Maybe before the end, I will just share a few last slides because I would like to announce our next meetup. Okay, so the next meetup will be in January, and Jakub Bliźniuk, I think he's also one of the participants today, will give a talk about quantum safe cryptography. So I'm not sure if this will be the exact title. Probably the title will be a bit different, but the topic or the scope will be around quantum safe cryptography and in general security in quantum computing. Jakub, if you are with us, maybe you can say more if you want.
Yes, can you hear me?
Yes, I can hear you.
So yes, as you said, this talk will be focused on how quantum computers impact cryptography, and well, it's related to security in general, but I will be focusing on cryptography and what are we doing with it. So, as mentioned, post-quantum cryptography, what's the state of that? How are the competitions developing, for example? There will be more on that later. Yes.
Okay, great. So we are looking forward to this meetup, and we hope everyone will join us as well. Okay, and finally, we would like to thank once again our strategic partners, Cogit, Snart, and Sonovero R&D, as well as our honorary partners for supporting us. Do we have... Okay, so some links if you want to stay in touch. Feel free to join our Facebook group or our mailing list, follow our Facebook, Twitter, X, LinkedIn profiles, our YouTube channel, where we'll hopefully upload the video recording from today. So let's stay in touch, and thanks to that, you will learn about our next events. All right. Thank you once again. Thanks, Karol. Thanks, everyone, for joining. And we hope to see you next time. Have a good Christmas break. Hopefully, Merry Christmas, everyone. And we'll meet each other again in the next year.